Hi, everyone. Today's Monday, 10th of February, 2025. This is the All Lab Script Reading Group. I have a slightly longer range this time. So first of all, I want to say that the Notion page for the seminar is now open and published on Notion. So it has like pretty layout, has a good description, and there is information how you can be added into the seminar. It has a log of all the previous talks with all the information and links to YouTube and so on. So I'll post it in the chat, but it will also appear. It will appear in future, and I will attach it to the future invitations. This is the link for those who are in the chat right now. So reminder about the format. It's the 1 hour, and we try to kind of keep it slightly more interactive. So feel free to ask questions, obviously, during the pauses or raise your hand if you're so not to interrupt the speaker. As I mentioned before, for now, use chat for necessary communication and not just chit chat. Yeah, otherwise, the presentation is recorded. I think that's everything I want to say about the format. We're very happy today to have Albert Garreta. Do I pronounce it correctly in terms of the stress?
Yeah, it's good. Yeah.
Okay. So Albert is a lead researcher at Nethermind since 2023, if I'm not mistaken. And previously, Albert was a postdoc at the Basque Center of Applied Mathematics and got his PhD from Stevens Institute of Technology, New Jersey, USA. Albert will be talking about several recent results regarding folding over groups and lattices. Yeah, correct me if I'm wrong. Highly relevant, interesting technique in zero knowledge. So with that being said, thanks a lot for coming, Albert. Welcome.
Yeah, it's a pleasure. Thanks for inviting me. So let's start with the basics. What's folding? So let's fix a relation R, which contains pairs XW as usual. X is an instance and W is a witness. And in a folding scheme, well, it's an interactive protocol between prover and verifier. And both prover and verifier have two instances of the relation. And the prover also has the witnesses, if the prover is honest, and they are valid witnesses. And then in this scheme, the prover and verifier interact. And at the end of the interaction, they output a new instance witness pair. The new witness is only known to the prover, and the new witness is known to P and V, so that, informally speaking, if this new instance witness pair is correct, then the initial two instance witness pairs are also correct, except with negligible probability. So this is folding in a nutshell. It's just taking the task of proving two instance witness pairs, and it transforms it into the task of proving one instance witness pair. And if this folding step is cheap, if it's cheaper than proving one instance witness pair, then you are saving work, right? Because you reduce the two tasks to one task at paying a price which is lower than the price of doing one task, right? Okay, so this is overview from 5,000 feet away. Now let's do 4,000 feet away. In most folding schemes, commitments are extremely important. And actually, one considers instances that contain a commitment to the witnesses. So really, we always have instances of this form. So the instance is X, which is X prime, so true public instance, and then a commitment to the witness. And then these boxes look like this. So you always have the commitments hanging around in the public instance part of the pairs. And in most schemes, this commitment is homomorphic, which means that the commitment of the sum of vectors is the sum of the commitments. There's some recent work. There's ARC and a previous work by Boons and some co-authors, if I'm not mistaken, that use non-homomorphic commitments and actually support hash-based commitments. But the usual thing is to have homomorphic commitments. Okay, so folding became very popular since Nova was introduced in 2021. There's been a lot of research influenced by this paper. In Nova, the relation being folded is the so-called committed relaxed R1CS relation, which looks mostly like this. It's not exactly this relation, but for the purposes of this talk, I simplified it. So there's a witness, which we split into two parts, Z and E, and then there's commitments to the witness. There's always a commitment to the witness in the public part. And then we have this R1CS constraint. So R1CS like constraint, right? So this would be an R1CS constraint, and there's this extra plus E here. And then these commitments that we have in the public instances must be valid. We also have this as constraints, obviously, otherwise this thing here is not doing anything. So this is how it looks visually. Oh, and A, B, and C are public matrices, often sparse. This is called error term. So Nova, the idea in Nova is very simple. You just take your two instance witness pairs and take a random linear combination of the witnesses, of the sets. Forget about the error terms, take a random linear combination of the sets, and then deal with the mess that you get. So, and you get a mess because if you take a random linear combination of Z1 and Z2 and you plug it in an R1CS relation, you're gonna get cross terms that create a mess. So what you do is you just say, okay, these cross terms are a new vector E, and you add this new vector to the relation. So I'm not gonna go into the details of why Nova works. I'll just describe it now. Going into the details and explaining exactly why it works would take too much time. So if you're not familiar with Nova, you will have to take my word for it that this is how it works. So this is a scheme. As I said, prover and verifier have two instances, and the prover also has the witnesses. And the first thing that the prover does is send a commitment T to some vector T, which is called cross-term vector. And then the verifier sends a challenge, and then they are done. The new Z3, is the random linear combination of Z1 and Z2 with alpha the randomness. And the new error vector has this form. If you compute, you make the computations, you get this, that the new error vector has this form. I will not go over it. You'll have to trust me. And now the verifier also needs to obtain the commitments to Z3 and E3, right? But this is very easy because if you are using a normomorphic commitment scheme, you see that E3 and Z3 are linear on E1, T, E2, and Z1, Z2. So you can just obtain the commitments to Z3 and E3 using the commitments to Z1, E1, and the commitment to T, using the linearity of the commitment scheme. So the verifier just computes the commitment to Z3 by making these computations in here. And this is correct because of the homomorphicity of the commitment scheme. Okay, so the vector T, we call it cross term. And committing to T is the bottleneck of Nova in most scenarios. And this is because T in general is filled with random field elements because it's related to this error term. And usually the commitment scheme in Nova is based on elliptic curve groups, which means that the field is relatively large, at least 256 bits. So this means that T is in general filled with group elements that have about 256 bits at least. So for typical parameters, this costs about 2 to the 8 times the size of T field multiplications, assuming that T has a size about 2 to the 20 entries. This is using Pippenger's algorithm for computing multiscalar multiplications. And yeah, so this becomes a big bottleneck, and especially if the actual witness Z1 and Z2 of your R1CS relation doesn't have big entries, which is often the case in many applications. So just to get an idea, if Z1, Z2 have small entries in them, then the cost of committing to this cross term in Nova is about is over 80% of the total cost of the folding time. So if you want to improve upon Nova's performance, you might want to take a look at this step in here, because it's mostly the entire cost. So let's see if we can remove this part in here. Let's first see, why does the prover need to commit to the cross term in the first place? Well, it's only because the verifier needs to compute the commitment to E3, right? And it computes the commitment to E3 by using this linear expression in here and the homomorphicity of the commitment scheme. And to do this, it needs to have the commitment to T. So that's why the prover needs to commit to T, it seems. Now, recall the definition of relaxed R1CS, or the not too formal definition I gave. It's this one, right? So the witness is valid if this constraint in here is satisfied. So a key observation we make is that E3 is implicitly committed by Z3. And this is because E3 is equal to this expression in here. So if you have committed to Z3, E3 is fixed, right? If you fix Z3, E3 is, there's no ambiguity. E3 is fixed also. So I'm not saying that Z3 is a commitment to E3, because it is not, formally speaking, but you can get around the need of having E3 committed by using the fact that E3 is uniquely determined by this expression in here, and which uses an element that is committed already. And you can prove that as far as folding pairs of relaxed R1CS instances. So as far as it goes, or when you want to fold instance witness pairs for the relaxed R1CS relation, you actually don't need the commitment to E3 at all. You can just remove it from the relation. And the prover doesn't need to send the commitment to the cross term. You can just you can forget about the commitment to E3 completely, and you'll get a sound knowledge sound folding scheme. However, that's not enough, because the committed R1CS relation by itself is not very interesting if you don't get relaxed R1CS instances that come from the R1CS relation. And let's see why. Yeah, so the standard R1CS relation is this one, and we have added the commitments, because in folding we always have the commitments in the instance part. So, and this is really what Nova wants to fold, because this is what we are interested in snarks, right? We are not really interested in relaxed R1CS relations. And Nova needs to go from the actual R1CS relation to the relaxed one because of these error terms that appear. And the way that it moves from the R1CS relation to the relaxed one is by simply adding an error term, which is forced to be 0. And it is forced to be 0 by having the commitment to this error term be the commitment to the 0 vector. Okay, so it moves from R1CS relation to relaxed one by adding the 0 vector, the 0 error term here. And it makes sure that this error term is 0, because it adds the constraint that the commitment to E is the commitment to the 0. So in here you would have a known commitment to the 0 vector. And this is how the verifier knows that the prover is using an error term which is 0. Right, Z. So the commitment to Z and Z is in the R1CS relation, if and only if this thing here is in the R1CS relation, where the commitment to E is the commitment to 0. Except with negligible probability if you have broken the binding property of the commitment scheme. But imagine we just remove the commitments to E and this constraint here. Then having that the commitment to Z and ZT is in R does not imply that the commitment to Z and Z is in R1CS, right? Because you can take any Z that doesn't satisfy this constraint in here, and then take this E here, which is not the 0 vector, because we are saying that Z doesn't satisfy this constraint. And then you get that this Z bar, ZE belongs to this modified relaxed R1CS. And this is really not interesting. It's a completely non-interesting relation. So we cannot just remove the commitment to E from the relaxed R1CS relation. Even though when you are actually folding inside relaxed R1CS relation, you don't need it. Okay, so this is the R1CS relation, and this is the relaxed one. The commitments to E are not needed if we only want to fold R. But we want to have a meaningful transition from this relation to this one in here. And if we remove these commitments from here, then this transition stops being meaningful and interesting. This is exactly what I explained. Oh, yeah.
Yeah.
Yes.
Albert, sorry, can I ask you a short question just to make sure I understand this correctly? So whenever you say that it's not necessary to include the commitment to E into the statement, you mean that you can just you could recombine the commitment to E by linearity over R1CS? Or this yes, I think so. R1CS is not linear, so I think this is where I'm getting confused. So you say that E is technically defined by that, but can you compute the commitment to E from commitment to Z? You cannot, right?
You cannot, but well, no, you cannot. But E in any case, so you can also not compute E, right, from the commitment to E.
Yeah.
So by seeing the commitment to Z, you are kind of seeing a commitment to E, because E is this thing minus ZZ. Yeah. So you can still argue binding. You can say you define E as the vector that results from computing AZ Hadamard product BZ minus ZZ. Okay, and then you have bindingness, and you say the commitment to this vector is the commitment to Z, and you can prove bindingness.
Okay, this makes sense. So I guess there is like a non-computational way to argue that the commitment to E is uniquely defined by the equation, yes, but there is no way to compute it. Okay. Thank you.
Yeah.
There was another question.
I've got another question, which is mostly on the relation, just to be sure. I guess there's gonna be a simplification later, but there is also a U to homogenize the constraints in relaxed R1. It's quite common in the computation of T. So if you remove U, then T depends on U, and E doesn't depend only on Z3. It depends also on a message sent by the verifier. So I just want to be sure that I'm missing something.
E3 depends on the message sent by the verifier, which is alpha and appears in here. And when you have the U, so this expression is the one you would have even if you add this slack term in here.
But T depends on U.
Yeah, it does. Yes, but I didn't write the actual expression for T, but it does depend on U. But in this definition, I just removed U for simplicity.
Okay, so
yeah.
Okay. Okay, so it's you're saying that's equivalent without the U?
No. It's not equivalent. This is like a simplified version of the relaxed R1CS relation, which I wrote just to remove symbols from the slides. It's not technically correct.
Okay.
So here there should be a U, and the U should be part of the public instance.
Okay.
And yeah, and then there should be also a vector of field elements, which is public, and Z, and then in here, instead of using Z to be this vector in here, Z would be this vector of field elements, and then a smaller witness, W.
Okay.
Yeah, but yeah, if adding this to the slides only adds technical overhead, and it doesn't really contribute to the ideas I'm explaining. So that's why I opted for removing it.
Thank you.
Okay, so we need the commitment to E when moving from the actual R1CS to this version of the relaxed R1CS relation. Or at least what we need to do is to ensure that the error term is 0 when we make this transition. We don't necessarily need to do it by committing to the error term. And this is what we do. Instead of using a commitment to the error term, we just evaluate the material extension of V at a random point. So we, given an instance witness pair for the R1CS relation, we create a new one for this relaxed relation by adding an error term and adding the constraint that the material extension of the error term at a random point chosen by the verifier is 0. And then if this is true, then it means that E is the 0 vector. And if E is the 0 vector, then if this thing satisfies this constraint, then AZ Hadamard BZ is ZZ. And we get this equivalence in here. So we take a new version of the relaxed R1CS relation, where instead of having the commitment to the error term, in here we have a field element V and a random point R. And then we replace the requirement that we replace the commitment constraint on the error term with this MLE evaluation claim in here. And the resulting scheme is, so now we just do, we try to do Nova, but for this relation, and we get this scheme. So prover and verifier know 2 instances. The prover also knows the witnesses. And now let's assume here that the evaluation points are the same. And I'll explain what we do if the evaluation points are different afterwards. So in the usual Nova scheme, the prover would send a commitment to T in this first step, in this first round of communication. But here, instead of committing to T, the prover sends the evaluation of the material extension of T at the random point R. So we are replacing commitments to error terms and cross terms by evaluations of the material extension at a random point that was sent by the verifier previously. Then the verifier replies with a uniformly sampled challenge, and then they are done. They output the new instance witness pair in a similar way as done in Nova. So the new Z is a linear combination of Z1 and Z2. The new error term has the same expression as the previous one. So Z3 E3 is just computed in the same way as in Nova. The new evaluation point is R, the one we started with. And the new value, so the new MLE evaluation value, is computed in the same way that the commitment to E3 would be computed, but using the evaluations of the MLEs of the E's and the evaluation of the MLE of the T. So in Nova here, we used to have commitment to E3 is equal to commitment to E1 plus alpha times commitment to T plus alpha squared times commitment to E3. And now in here we have MLE evaluation of E1 plus alpha, MLE evaluation of T plus alpha squared times MLE evaluation of E3. We just replace the commitments to error terms and cross terms by MLE evaluations. And if R1 is not R2, then we use a prior step, which is basically the GKR trick, where you reduce 2 claims about evaluations of MLE of multilinear polynomials into an evaluation at the same point. It's quite it's a somewhat standard trick. You create a line that passes through R1 and R2 and have the prover send the composition of the multilinear polynomials on this line. And then the verifier chooses a random point for the line, and you get new claims of evaluations for the two multilinear polynomials, but on the same point. It's described in Thaler's book in the GKR section, for example. You could also use the hypernova trick. In hypernova, there's also the issue that the prover and verifier want to reduce the evaluation of two MLEs at different points into the evaluation of an MLE into one point. And in hypernova, this is done using the SumCheck protocol. You could also do that. Okay, I'll also mention that Mova turned out to be very similar to Proto-Galaxy. So we could think of Mova as a particular instantiation of Proto-Galaxy, changing a bit after changing a bit the base in which polynomials are expressed. So you could say that Mova is kind of a rediscovery of a part of Proto-Galaxy, some aspects of Proto-Galaxy. Okay, so in terms of performance, this is how Mova compares to Nova and Hypernova. So it's assuming that, so these are prover times. We assume that the witnesses contain small entries. If the witnesses don't contain small entries, the gains are not that big. But in this case, the gains are about 5x. In some configurations, they are even 10x. And they are about 3x with respect to Hypernova. This is tested in a single core. We used identity matrices for the R1CS relation. Verifier is similar to Hypernovas. Yeah, so these times for Hypernova come from a non-optimized library from the Sonove library by PSC. There's some literature on how to improve Hypernova's performance. I think it's not implemented. I'm not sure. At least when we published the paper, it wasn't, because those improvements just came out. But we did count the amount of field multiplications of Mova and this improved Hypernova version, and still Mova performs about 1.2 to 1.4 better than Hypernova. So we don't actually have benchmarks. We counted the number of field multiplications. Okay, so let's go back to discussing folding schemes and the commitments. As I mentioned, usually the commitment in folding schemes is based on elliptic curve groups, and it's usually either the Pedersen scheme or KZG. And this has some inconveniences. First is that the vectors being committed live in a big field, and you are kind of bound to work in a big field. And commitment can be very expensive, as I mentioned. We were discussing the cost of committing to a cross term full of arbitrarily large elements in the field. It's difficult to recurse over, because when you want to prove that folding was performed correctly, then you have to arithmetize elliptic curve group operations in your snark. And as I said, if you are using Pedersen or KZG to fold, then when you want to prove the folded instance, you are kind of bound to using a KZG-based snark. You could try to change the snark, but it would be complicated, and you would have to arithmetize statements about KZG committing, and you would have to prove those. So an alternative is to work with lattice-based commitments. And yeah, so now I'm gonna give a crash course on lattices, and then I'll explain why lattice-based commitments are interesting in context of folding. Okay, so a cyclotomic ring is a ring of this form. You take the ring of polynomials with coefficients in a finite field, and you quotient by certain polynomial, cyclotomic polynomial. This gives you the set of all polynomials of degree at most d, where d is the degree of f. And you can think that fx is, for example, x to the power of 2 plus 1. But you can choose other f's. And then we have a very nice decomposition. So R is actually just the direct product of several field extensions of FQ. This isomorphism, we call it NTT, number theoretical transform. It comes from the Chinese remainder theorem. You write the factorization of F into irreducible components, and this gives you this decomposition. And the number of factors you have here and the degree of the extensions depend on the exact polynomial you choose and the prime. And an important thing, if you want to prove statements over a field using lattice-based cryptography, is that you can actually pack several field elements into a ring. So you can think of every ring element as tau field elements, right? So imagine if you have a trace and the trace contains field elements, you can create packs of tau field elements and put them in a single ring. You just take tau field elements that are in the trace, you put them here, and then you apply the inverse of the entity, and you get a ring element. So we think of ring elements as packs of tau trace cells, for example. Okay, so there's this commitment scheme over these rings, which is called ITI commitment scheme. It's 4 vectors of ring elements, and it works as follows. So as parameters, you take a matrix of certain dimension. It has to have m rows, so the dimension of the vectors you want to commit to, and you sample it uniformly at random. And then the commitment to a vector from Rm is just the matrix multiplication of A, matrix vector multiplication of A and B. And we can sort of see that it is homomorphic because the commitment to a vector is just matrix multiplication. There is a big caveat that I'll discuss in a second. Something that I think is interesting about these commitments and this setting is that you can actually take FQ to be a small field and actually a field relevant for the snark world. So for example, you can take FQ to be the Goldilocks field or the baby bear field or the big star prime. I'm not sure about what's going on with M31. I think we didn't figure it out, but it might be possible. As I said, it's very nice that each ring element can pack tau field elements, and that's very important when taking into account when evaluating the performance of these schemes. And it should be relatively cheap to arithmetize statements about commitments over FQ. So imagine you have your snark that works over baby bear, like Plonky 3, and you want to work with ITI commitments. You can take a ring where FQ is baby bear, and if you want to prove that something is committed correctly, you just have to write these operations as operations over FQ, right? And which is basically, so you can think of every entry of A as a tuple of field elements from an extension of baby bear, and V again is a vector with tuples of field elements from baby bear. So this should be relatively cheap to arithmetize. There shouldn't be too big of a cost. I don't know. I don't have numbers, but intuitively it sounds much better than arithmetizing group operations over baby bear.
Yeah, sorry. There's a question from.
Yeah.
The question is how large should I think the kappa is of lambda?
Yeah, kappa is about 8 to 16 in our configurations. So a configuration we keep using is Goldilocks. So we use the Goldilocks field FQ with kappa between 8 to 16, and we have tau 8 tau is equal to 8, and t is 3. So we have degree 3 extensions of Goldilocks, and there's 8 copies. And kappa is between 8 and 16. Sure. And actually, committing I-type commitments are really cheap, actually. You can see in the abstract, I linked a document with a lot of benchmarks with lots of parameters. You can check them out. They are cheaper than Merkle tree commitments when you are using algebraic hashes. Okay, so that's one point, one aspect why we are interested in lattice-based folding. It's because it is much more amenable to being used in the context of Starks in the context of Starks, hash-based schemes, and so on. And the other is because it's post-quantum secure, or at least plausibly. So let's see how we can fold with these commitments and in this setting. And let's work on a toy scheme. So let's define a toy relation where we have the instance is a commitment and the witness is just a vector. And the instance witness pair is correct if the commitment is actually a commitment to the vector. And we let the commitment be a homomorphic commitment scheme, say Pedersen, and we will change it to I-type commitments afterwards. And now the scheme works like this. So the verifier sends a random element, and then the prover and verifier just take a random linear combination of the initial two witnesses and the commitments using the verifier's challenge. And it's clear that this is correct because of the homomorphicity of the commitment. Okay, so let's look at this scheme once we instantiate it with the I-type commitment. So this is a reminder of what the I-type commitment is. And now is the time for me to give you the caveat of the commitment. The I-type commitment is only binding when the vector has small norm. And by norm, I mean the largest coefficient of an entry in the vector. If we look at at entries in vector as polynomials in F-cube, reduced modulo F. So if we instantiate the toy folding scheme with the I-type commitment, first we have this relation. So I just replaced the abstract commitment that was written before by the I-type commitment. And okay, so this is not going to work. This doesn't make much sense because this commitment is only binding when the witness has small norm, right? So we have to start by modifying the relation and ask that what's being committed has small norm. So let's consider this relation in here. Just place a constraint asking that the witness has small norm. And in case that the prover wants to use a witness with larger norm to enable completeness, we can have the prover decompose the witness into low norm chunks and commit to each of them. But let's analyze how we would fold this relation. Okay, so we fixed two instance witness pair in this relation, and now the toy folding scheme would look as follows. The verifier sends a challenge alpha in the ring, and then the output is just linear combination of the two witnesses and the commitments. Okay, so this looks okay-ish, but there's actually two very big problems. One is regarding completeness. So W3 if W1 and W2 have norm at most B, the random linear combination of W1 and W2 in general doesn't have small norm, right? It can have arbitrary norm, especially if you sample an arbitrary challenge. So this this new instance witness pair is no longer in the relation, even if the prover is honest. So you don't have completeness. We lost completeness. And there's a big soundness problem also, which is to prove knowledge, to prove soundness, to prove knowledge soundness, you have to design a extractor that if a malicious prover is able to convince the verifier, then the extractor is able to output witnesses for the initial instances that are in the relation, right? So in particular, the extractor has to output witnesses with small norm. But the way this scheme is written, so there's no apparent way you can guarantee this. And these are the two main challenges that have to be solved when you want to fold over lattices. And Dan Bonnet and Binyi Chen solved these challenges last year in the following way. So regarding the norm increase problem, which is that when you take the random linear combination of the witnesses, you might have big norm. Dan and Binyi proposed to decompose each witness into, say, radix 2. So just decompose the two witnesses into small chunks, say chunks that have norm less than 2. And then you have the prover send commitments to each chunk, and the verifier sends challenges, one challenge for each chunk. And these challenges belong to certain subset of the ring, which I'll describe a bit more in a moment. And then the output is just the random linear combination of the chunks and the commitments. And crucially, these challenges are sampled from a subset of the ring that guarantees that this output witness has small norm, assuming that the prover was honest and that the witnesses had norm at most 2. So yeah, you can think that they are challenges with the special property that make vectors make elements not grow in norm too much. So if the prover is honest, then the folded instant witness pair is in RB, and we have completeness now. Yeah, and this is a bit delicate, so there's lots of parameters in play. One has to be a bit careful to choose the parameters correctly so that this set C is large enough and so on, and you still have efficiency. You don't have a big kappa or other possible issues. Okay, the other problem was that there's no apparent way to guarantee that the prover is actually using low norm witnesses. So here I added this sentence. Assuming that the prover is using low norm witnesses, you get that the folded instance witness pair is indeed in RB. But this is not enforced right now. So we have to do something. What is done in LatticeFold is that this constraint in here, so W, the witness has a small norm. Bonnet and Chen replace this constraint by a grand product constraint, which looks like this. And let's unpack it. So here we have the expression coefficient of W. This is just the matrix of the coefficients of the entries of W. Let's see an example. So if W is this vector with these two ring elements, then coefficient of W is just a 2x2 matrix. The first row contains the coefficients of the first entry of the witness, and the second row contains the coefficients of the second entry of the witness. And here you are just taking the product of this matrix minus a matrix filled with the number J. And you are asking that this product, you make J range from minus B to B, and you ask that this product is 0. And this can only happen if all the entries of this matrix are between B and minus B. If you can think that this matrix is just one field element, one one field element. If this matrix is just one field element, and this ID is just the number 1, then it's clear that this field element is between -b and b, right? And this is done component-wise. I guess this should be Hadamard product, not this product in here. So this is our component-wise product. This is done component-wise, so the same reasoning applies to each component of the matrices you have in here. And
Sorry,
yes,
but just what I wanted to ask. So the equation itself is like on matrices, right? So you subtract from CoFW minus JID, and the product is what? So how does product define as a component-wise product? And the 0 on the right side is also a matrix.
Yes, correct.
So basically, for this equation to pass, you need to have at least 0 in every component in one of the terms.
Yes, exactly.
Okay, I see.
Yeah.
And if there is an element that is bigger than b, then there will not be a 0 in that.
No, there won't, right? Because each factor will be non-zero.
Yeah. Okay, makes sense.
Yeah, it's really easy to see if CoFW is just one element, if we don't have matrices. And then once you are convinced that if you don't have matrices, this ensures that this element in here is between b and -b, then extending to matrices is relatively straightforward. Yes, Mark?
Yes. So you're saying this is the Hadamard product.
Yes, this should be Hadamard product.
So for it to be zeros, it means that one of the term need to be. Sorry, I'm a bit confused because CoFW is not a diagonal matrix, but J times ID is obviously diagonal.
Oh,
so,
yeah, this should be the. Yeah,
like
sorry, this should be the.
Yeah, sorry, go ahead.
This should be the matrix that's filled with ones, not the ID matrix. Sorry.
Oh, okay, thank you.
Yeah. Sorry. This should be matrix filled with ones. This should be Hadamard product, and this is a matrix filled with zeros. Thanks for the question. It's good that I got to clarify this. Yes, Danny?
Yeah, sorry, I'm just going to repeat to be sure. So ID is really the matrix if only one is full. If W is like 3, it's only 1. There is no 0, only 1. And so you got minus J times 1 on the whole matrix. So yes, okay. I see you yes with your head, so I guess.
No, I didn't get the question, sorry.
Oh, ID is really is not the identity matrix, as Mark said. It's really just 1 everywhere.
Yes.
Okay.
Yeah. Okay, so you replace this inequality by this algebraic expression, grand product, and these are equivalent if you write them correctly and don't write ID or weird stuff. And then this is just a grand product constraint, and we know how to treat them. You can treat them with sum check, and that's what is done in LatticeFold. They perform a sum check on this grand product constraint, and the grand product constraint gets reduced to an evaluation claim about a multilinear polynomial. And if you do this step when you are folding, this is sufficient to ensure that the witness being used by the prover is correct, assuming that the folded instance witness pair is correct. So it allows the extractor to output witnesses with small norm. And then the authors expand this idea, because the authors actually start with the toy relation I explained and design a folding scheme for that relation. And then they expand it to a Hypernova style folding scheme for CCS constraints over lattices. And there's some technical tricks in the paper where you don't actually use the coefficient matrix. You use some tricks related to entity to pack elements together so that your matrices are a bit smaller. But for the purposes of this talk, this is really not necessary. And yeah. Okay, so we actually implemented LatticeFold. We released the repo about a month ago. These are some numbers we got. As I mentioned, we have a super detailed benchmark report. It's huge. There's lots of parameters, lots of things being measured. this is just the tip of the iceberg of the benchmark report. So let's look at some times. So this is the size of the CCS witness in ring elements that is being folded, and this is the equivalent size if you count the number of field elements in entity form. So if you are, for example, using a 2 to the 13 witness size in a cyclotomic ring that splits into 8 factors, you are really folding witnesses with 2 to the 16 field elements because of the packing technique I explained before. So if you want to compare LatticeFold with Hypernova, you should take 2 to the 13 for LatticeFold and 2 to the 16 for Hypernova, because Hypernova uses vectors of field elements and LatticeFold vectors of ring elements. So we get this performance. Yeah, so I think we ran the benchmarks in a relatively not powerful machine because these Hypernova prover times are quite large for these parameters. Previously, I compared Mova with Hypernova, and there was the 2 to the 16 setting, and we got about 200 milliseconds for Hypernova. So definitely, these experiments are run on a relatively slow machine. But I guess that what matters is the actual comparison here, the relative performance difference. So LatticeFold is slower than Hypernova. The main cost in LatticeFold comes from the sum check step, so from reducing the grand product argument into polynomial evaluation claims. And one of the questions we are researching is whether we can do lattice-based folding without it. We have an answer. It's working. So we have an answer. It's not published yet, but the answer is yes. So what we want to do is design a lattice-based version of Nova or Mova in order to avoid the sum check step. And actually, Mova was developed while we were trying to answer this question. And so we were trying to solve this question, and we came up with Mova over lattices, and we thought that it had interest on its own as a folding scheme for over fields with group-based cryptography. And I guess we are close to time, so I will not explain our solution here, I guess. I think I have like 3 slides left, but they are quite packed.
Yeah, I think, Albert, that would be a good idea. I'm sorry. Yes, maybe it's a bit,
sure.
bit short in time, so would be better to ask people to ask questions. For that. Yeah, thanks, Albert. If anyone has any questions to Albert, it's a good time to ask them. I think we have like a bit of time. We can go like several minutes over time.
Yeah, Giacomo?
Yes, hi. Thanks for the talk. Just a question. So you said the main of the overhead of like LatticeFold over Hypernova is due to the sum check. Is that because, like the high degree of the sum check? Is it because the ring arithmetic is lower? Where does it? Because Hypernova also has a sum check in it, right? Or am I?
Yes, but the thing is that it's not the degree, because the degree is low if you decompose into chunks of small norm, right? Because you are doing the sum check over a grand product. So if you decompose into chunks of norm, say at most 2, then the degree is 3. The issue is that there's the actual polynomial has lots of terms. It has like the number of chunks, 2 times the number of chunks terms, each of degree 3.
Yeah.
So it's
a trade-off in how many chunks you want to split things in and how large the composition is at each point.
Yeah, exactly. But in any case, you always end up with a polynomial with either a high degree or a lot of terms, and this creates a painful sum check.
Okay.
On the other hand, Hypernova performs a sum check on a much simpler polynomial.
So it's just a quantized something, I guess. Okay, thank you.
Yeah, sure.
I might have a very short question and several maybe questions. So a short question is like, even with the LatticeFold trick, I assume the norm underneath is growing, right? So it does just grow at the polynomial speed. So the norm of the folded, elements, the norm of the committed element is still growing, just growing like not fast enough for any polynomial amount of folds we want to perform, right?
Yeah, exactly. If you want to fold again, in principle, you have to decompose again and fold again. Though it is possible that if you know you are going to fold 10 times, maybe you can ensure that the norm will never grow enough so that you have to decompose again. And maybe you can skip that step. And that would actually cheapen things a lot, because you wouldn't have to create all those chunks and you wouldn't have that sum check over a huge polynomial with the number of chunks terms.
Okay, this makes sense. I have another question if no one wants to interrupt me. So I guess the presentation was like composed of 2 parts, and I'm kind of curious about the transition from the first to second part. So Mova can be used with many commitment schemes, right? But for efficiently using the GKR protocol to do this, to replace the commitment with a check, you need a commitment scheme that works natively with multilinear extensions, right? So this is why. So which commitment schemes are actually useful with Mova, just Mova itself? Like which commitment schemes are compatible enough?
I would say multilinear. So you don't need multilinear polynomials to apply the GKR trick for sure, or to apply the sum check trick from Hypernova to reduce the evaluation of two polynomials at different points into one. So for sure, it looks like you need multilinear polynomials, but there might be some way to work with univariate ones. So the question you have to answer is, given 2 evaluation claims of univariate polynomials at 2 different points, how do you create an equivalent 2 evaluation claims at the same point? If you can do this, then you can do Mova with univariate polynomial commitment schemes. I think actually Giacomo asked me this question some time ago.
Oh, sorry, I maybe didn't read it. Okay, sorry.
No, I mean a very long time ago. No.
Yeah, before October or something like that.
Yeah.
We have a way to do it probably, but it's still somewhere in some paper that eventually will come out eventually.
Okay, and then I guess my kind of more generic question is that in terms of like Nethermind research and products, how do you see this? Like what exactly? So you're working over lattice commitments, and you're doing, you're developing the toolkit for folding over lattice commitments. But what do you use it for? Like how do you what kind of proving system do you use on top? Like that it should be compatible with lattice commitments as well. So I'm kind of curious.
Our goal is to enable efficient folding in the context of Starks. So we want to eventually, be using a Stark scheme and also be able to fold without and do it and fold cheaply. I have a couple talks explaining how we are planning to do this. In one talk at ZK Summit and another in DEF CON, if someone is interested.
That sounds quite interesting indeed. Okay, I think we're a bit over time, so I would suggest to wrap up unless someone has a question. No. Okay, then once again, thank you a lot, Albert, and I'll stop the presentation right now. Thanks a lot.
Thanks for the attention. It was a pleasure.